talk about on some inequalities in quantum information theory. My plan is to keep most of the talk at a general level, and later on I'll talk about some specialized topics, but that will be at the later part of the talk. So I would like to carry the audience along with me, so feel free to ask me any questions, feel free to interrupt me, and don't hesitate in doing so. Okay, so let me start. So let me start with the quantum states, and I'm going to, as I said, I'm going to talk about pretty basic stuff to start with. So a quantum state is described by a ket, which is a unit column vector. It's a column vector with a unit norm, and we are going to denote it by psi with this kind of a symbol here. And the only operations which are allowed are unitary transformations. You can multiply this column vector psi, ket psi, with a unitary matrix. And a unitary matrix is that if you multiply with its dagger, which is the conjugate transpose, you get an identity matrix. So psi can go to u times psi. Now, let's make it a little more complicated. Let's say you have an ensemble. So what happens in an ensemble is that you don't know that the state is psi, but what you know is that the state is psi sub I with probability p sub I. That's the only thing you know, and I varies from 1 to, let's say, k, where k is a finite number. Now for an ensemble, which we denote it like this, p sub I ket psi sub I, the state can be described by a density matrix, and the density matrix is given by this summation over here. And I mean, this is a convenient representation. You could as well work with the ensemble here with the probabilities and the associated kets, but this is a convenient representation, and so most of the time that's what is preferred, and that's called the density matrix. Now density matrix rho is a positive semi-definite matrix with the unit trace, and it's quite clear from here because p sub I is a probability vector, so the trace is 1 and it's a positive semi-definite because of the form here. And the unitary transformation by u, which is the unitary matrix, on rho, that would result in multiplication by u from the left and by u dagger from the right. Now let's add, let's deal with the composite systems here. So suppose, assume that the quantum system of interest is A, and let the density matrix of the composite system AB be given by rho sub AB. Now the density matrix of A can be obtained by taking a partial trace over B, and you just take a partial trace here, where trace sub B over here, it indicates the partial trace over B. Now why this happens? I mean, you can of course derive this from the postulates of quantum mechanics, and just by trying to come up with a new density matrix which would have the same measurement statistics as you would expect by using the bigger density matrix. So I'm not going to do that here, but that's basically the way you get it. Partial trace also has a nice interpretation. If you have a, if this indicates rho sub AB, and let's say this is a Mn by Mn matrix, then you can divide this matrix you can write it as a so each of them is a n by n matrix. Sorry. And so this would be a m by m block matrix. Now the partial trace, what it would do is it would take a trace of all these matrices and it would replace each of these block matrices by its trace. And again, why it happens, you have to go through that exercise. It's not a very difficult exercise. It follows from the postulates. And that would be an interpretation for the partial trace. Another way of looking at it is that if you were to look at two random variables, let's say x and y, and they have a joint probability distribution. Now you want to get the distribution of x here. So what you would do is you would just integrate out y, and you would get the probability distribution, in this case the probability density function of x. So something you could understand something similar which is going here, that by taking the partial trace you are tracing out b, or you are integrating over b. Now the unitary transformation acts on the composite system AB, and suppose our rho AB has this special form. I'll mention in a moment why you need such a special form, or why you want to have that. And so what it means is that you're taking a tensor product of the density matrix of A, and the density matrix of B here in this case is a pure state. So I didn't define a pure state. A pure state basically is a special case of ensemble where one of the p sub i's, which I talked about in the previous slide, is 1, and rest all of them are zeros. So over here you are sure that one of the, let's say I equal to 1, you are sure that with probability 1 your state is ket psi sub 1 and rest are all zeros. So that would be a pure state. And if there are more than one i's for which p sub I is non-zero, so that would be a mixed state. So in this case we are taking a special form of rho sub AB, where the density matrix of B is this pure state, and it's written as a tensor product of the density matrix of matrices of A and B. Now if we apply the unitary transformation here, then the new density matrix of A is given by this. Basically we are first taking the unitary transformation, and the unitary acts on the composite system A and B, and after that we are just tracing out B. So that gives us taking the partial trace over B after you have applied the unitary transformation. And if you simplify this, this is not a difficult exercise, it comes out to be of this form. And where E sub k, they can be written like this, where j sub ket say j sub b is any orthonormal basis in B, and they also satisfy this criterion, which is also called the trace preserving condition. This again is not very difficult to see. And you can show that the partial trace in fact can be written as where I sub A is the identity matrix over A, and now I can just break this apart, and what I'll get is and this I call as the eqs, and you can show that the similar thing happens on the other side, so I can write it as eq dagger. So why is this an additional complication? Because in the previous slide I just said that the only operations which are allowed are the unitary transformations here. So life was simple here, and it became a little more complicated when we introduced an ensemble. It became instead of going from ket psi to u times ket psi, it went from rho to u rho u dagger. So things were simple. Now why the hell things are becoming a little more complicated here? The answer to that question is that basically our unitary is acting on the composite system AB. It's not acting just on A. And when it's acting on AB, and after that when you take the partial trace, it reduces to this form. But the good news is this is as complicated as it can get. It can't get any more complicated than this. So this is the most general quantum operation. And the EKs, they are also known as the cross operators. Yeah, so I should also mention that when I write it as a quantum operation, I write this with this calligraphic E, which acts on rho sub A, and it gives you this quantum operation. Now this E is also is a completely positive trace preserving quantum operation. So what do we mean by that? It's completely positive because if we take a super operator, so this quantum operation is also called a super operator. If we take a quantum operation of this form, I haven't defined that what this form is. Basically, if this kind of a operation acts on again on a composite system, and when you take the density matrix, you have to take its spectral decomposition, and then you have to take the Schmidt of its eigenvectors, and then you can apply this operation over that. Usually in many cases it simplifies. So this kind of a operation, it outputs a positive matrix for every positive input, and where I is the identity operation of arbitrary dimension. And actually this follows quite easily. It's not difficult to show that when you have a cross operation or cross operators like this, or a cross representation like this, it is going to be completely positive. And the TP over here in CPTP, it implies that the trace of the output is same as the trace of the input. And that's easy to show. That's pretty straightforward because of this condition. This basically ensures that the trace of this quantity is the same as the trace of rho sub A, because you just take the trace here, and then using the fact that trace ABC is equal to trace CAB, you take the EK dagger on this side and you take the summation inside, and you will get the trace to be the same. Yeah. So let's start with quantum entropy and relative entropy. This is what I'm going to do in most of this talk. Only in the later part of the talk, I'm going to talk about some selected topics. So let's start by the definition here. The von Neumann entropy for a density matrix rho is given by minus trace rho log rho. Now I should be corrected if I'm wrong. This definition, it actually precedes the Shannon entropy, although Shannon entropy is, I mean, a lot more people know about Shannon entropy than the von Neumann entropy. And I think it predates it by probably 2 decades or so, if not more. And another interesting thing is that I'm going to talk about the operational meaning of the von Neumann entropy. When Shannon defined his entropy, he gave the operational definition in his seminal paper. But the operational definition for von Neumann entropy, it came in 1995. I'll also quickly define the quantum relative entropy. So, Umegaki, he defined the quantum relative entropy of rho to sigma as this particular quantity, and where rho and sigma, they are the density matrices. And we could also write in this particular convenient form the von Neumann entropy. You can write it in terms of relative entropy. It's a simple observation, because if you put I here, the log of I would be 0. And the way you interpret the log here is, log here would be a matrix valued function. Its argument is a matrix, output is also matrix. So, it acts on the eigenvalues and it leaves the eigenvectors intact. And this simple observation which is there, we'll see that actually you could use many of the results of the relative entropy to prove the results for von Neumann entropy. In some cases, the proofs become much easier. So, actually, this is in 1995. Schumacher's quantum noiseless coding theorem gives an information theoretic interpretation to the von Neumann entropy. And this is basically, it's not a very formal way of stating AEP, it's loosely stated, but I hope you get the idea. So, the asymptotic equipartition property, or the AEP, it states that in the limit of a large number, let us say n, of identical repetitions of a random experiment with probability that can be made arbitrarily close to 1 by increasing n, the outcomes, they come from a typical set whose each member is almost equilikely. Now, and this property, it basically, it forms the basis for the classical and quantum data compression. Now, I don't want to spend too much time on it, but if you are not familiar, I know it can be a little bit of, it can be a little intimidating, but I mean, I won't be able to spend too much time on it, or any time on it. So, let us say if we are given n independent copies of the density matrix rho, so that means that we are given rho tensored with itself n times, then the typical set has dimension which is nearly 2 to the power the von Neumann entropy multiplied by n. So, suppose that our rho is a d by d density matrix, then we can compress its n copies to a 2 to the power s rho times n dimensional subspace, and then uncompress it back such that the fidelity of the input and the output can be made arbitrarily close to 1 by increasing n. And this was also mentioned by Graham Smith yesterday in his talk. So, there is a equivalent or there is a similar question which people in classical information theory asked, and that result has a quantum generalization also, and which gives a information theoretic interpretation to von Neumann entropy. So, let us first start by looking at some of the properties of the quantum relative entropy. The first thing is the Klein's inequality. So, what it states is that for density matrix rho and sigma, the relative entropy is greater than or equal to 0 with equality if and only if rho is equal to sigma. This complication which I entered over here, I'll mention it very shortly why I entered it, and actually there need to be a minus sign here, but it does not matter in this case for density matrices, but you can just ignore it. I should have probably deleted that. So, the quantum relative entropy is non-negative with equality if and only if both the density matrices are same. And this can be actually proved in not too complicated way by using the strict concavity of the log and using the log sum inequality, which is given by this. And that's a pretty well known inequality where a sub I and b sub I, they are greater than or equal to 0, and the equality holds if and only if a sub I divided by b sub I is a constant for all I. Now, Lindblad, or I don't know if I am pronouncing his name correctly, he proved the monotonicity of the quantum relative entropy, which is stated like this. So, you take two density matrices in the composite system AB, one is rho sub AB, another is sigma sub AB, and you take the relative entropy of both of them of rho to sigma, and now you take the partial trace over B for both the density matrices, and then you compute the relative entropy of rho sub A to sigma sub A, and this relation holds. Now, these guys, Ibbenson, Linden and Winter, they showed that monotonicity under restrictions is the only general inequality satisfied by the quantum relative entropy. It is a pretty nice result. I wish I had a result like that. It's a fantastic result. And in fact, many of the properties I'm going to talk about, I'll actually mention or I'll show that they can be derived from monotonicity. And these guys, Petz and Ruskay, they gave the equality conditions for the quantum relative entropy under monotonicity. So, they actually gave conditions for what properties these density matrices need to satisfy, such that the summations of these projectors is equal to I, which is the completeness relation. And so, what this statement means here is that your von Neumann entropy would increase after you hit it with these projectors. And the equality holds if and only if after you apply the projectors, that would give you the same state as before. And this is not difficult to show, it follows from monotonicity, because that small thing which I mentioned, small observation, that basically, and using that and the monotonicity, you can easily show this, because you can write von Neumann entropy in terms of the quantum relative entropy, and I can replace the I by, and then I just apply the monotonicity here. Another property that let rho sub I be a set of density matrices with same dimensions, and let their spectral decompositions be given by this. The spectral decomposition, as I mentioned before, means that well, it is a positive semi-definite, so it is a normal matrix, so it has a spectral decomposition, but in more simple words, what it means is that these guys over here are the eigenvalues of rho sub I, and the ket over here is just the eigenvector. And this different looking symbol is just a conjugate transpose of the ket. It has a funny name, so I won't mention that. And then for any probability vector p sub I, you have this relation over here. So, let us just go through. This particular relationship is just the concavity of von Neumann entropy. And then you have an upper bound as well, where you have h of p sub I, the whole vector, which is the Shannon entropy. So, that would mean minus summation of over I of pi log pi. and the equality in this particular inequality, it holds if and only if rho sub i's with pi greater than 0 are identical, and over here it holds if and only if rho sub i's they have support on orthogonal subspaces. I'm going to mention something, a very easy way of looking at this. This I won't mention in the next slide. So, the first inequality, it can be rewritten as this kind of thing. So, let us go back. This inequality you can rewrite like this. And now, using the Klein's inequality, all these are non-negative because it is quantum relative entropy. So, therefore, it's the whole summation is greater than or equal to 0 because you are just taking a convex mixture of these things. And now you can use the equality conditions of the Klein's inequality and you can get the required result. So, these three lines they only pertain to the equality conditions, but this thing holds for any rho sub i's. So, let us talk about some data processing inequalities, and they should not be generalized here because again I cut and pasted from some other presentation where it was generalized. Here it is not generalized. The question is, and this is loosely worded, very loosely worded. Yesterday in Graham Smith's talk he defined it much better. But hopefully you can get some idea using this, looking at this loosely worded statement. So, the question is that how many qubits can be transmitted across a given quantum channel such that the fidelity between the reconstructed qubits and the transmitted qubits can be made arbitrarily close to 1. Now, actually you should be asking these questions instead of, in terms of the log of the dimension. But of a subspace, but as I said it is loosely worded, but hopefully I can get some idea across. And also the maximization which we are doing is per channel use. So, it is not that you can increase the number of channel uses, then of course the number of qubits you can transmit would go to infinity, but it is per channel use. Now, suppose the answer is I, capital I, and it is a measure of information about the transmitted qubits which we can extract from the received density matrix. Now, what the data processing inequality, it states that I cannot be increased by applying any quantum operation on the received density matrix. And this is to be expected because I mean if you were to increase your I by applying a quantum operation, that would mean that that you can extract more information from the received signal about the transmitted signal by just massaging the signal more, and this goes against our intuition, and actually it can be mathematically proved also. What Shannon showed was, and the results carry over to the quantum case, that the data rate across a channel is not limited by the kind of computations you can do. It's not that if you put a supercomputer at your receiver or instead of your mobile you have a supercomputer, you can increase the data rate. It's actually fundamentally it's limited by the channel. And so these data processing inequalities, they give a mathematical version of what I just said. And for the quantum case, Peter Shor, he answered the above question, and he showed that I is actually the coherent information. And as was shown by Graham Smith, there is single letter characterizations are not possible in most channels, but I am not going to talk about it. I am just going to define what coherent information is, and I am just going to talk about the data processing inequality. So, suppose your system of interest is Q, and Q has a density matrix rho, and you have an ancilla R, R is over here, and that purifies Q. So what that means is that if your the composite the state of the composite system RQ is a pure state, it's given by ket psi superscript RQ, and then you take the trace over R and you are going to get back rho, which is the state of our system Q, which is the system of interest. And now you add this ancilla E1 and E2, and why you want to add it is that if you remember the previous slides, your quantum we want to mock up our quantum operations, this calligraphic E1 and calligraphic E2, and that they are mocked up by introducing these two ancillae E1 and E2. So you have E1 here, this is in a pure state which has no correlation with Q, it's a tensor product right now. Then you add the you have the unitary transformation, and that gives you the calligraphic E1, and then you have E2, and then you apply U2 over there. And the dashes indicate the state after you apply U1, and double dash after you apply U2. And U2 acts only over this over Q dash and E2 dash, whereas U1 acts over Q and E1. It leaves E2 unchanged and U2 leaves E1 dash unchanged. Now here is a convenient definition. I find this quite convenient. It's a definition of a coherent information, and if you were to look it up with coherent information, you can of course write it in various forms, but I find this form quite convenient, although if you ask me for intuition I may not be able to give you, but the intuition basically comes from Peter Shor's proof, I think. I mean that gives you the operational meaning to this quantity. So once you define it like this, then what the data processing inequality says is that for any two CPTP operations E1 and E2, and well I do not need strictly positive here, for any density matrix rho you have this inequality. And actually this inequality it follows directly by using the monotonicity here. That is why this definition is quite convenient. It just comes from the monotonicity. It's extremely easy to prove using monotonicity. But if you, I mean of course you can do the hard way, and many of the books they do the hard way. Let me talk briefly about the Fano inequality. Let's talk about classical Fano inequality first, CFI. It provides an upper bound to the conditional entropy of two correlated random variables, and let us say these random variables are x and y. So what do I mean by this? So suppose we want to obtain an estimate of x when y is known. So to get an estimate of x, we compute a function of y, which we denote by x hat. And let us say n be the cardinality of the set from which x takes values. And we are talking about discrete random variables here. So they have a probability mass function. So that is why n indicates the cardinality of the set on which x takes values. Now what the classical Fano inequality does is it upper bounds the conditional Shannon entropy of x given y, which we denote it like this. I add a subscript of s here because it is a Shannon conditional entropy by a function of probability of success, which is defined as the probability that x hat is equal to x. Now the classical Fano inequality is given by this number here. So you have the conditional entropy of x given y, that is upper bounded by the binary entropy function of p sub s, where p sub s is the probability of success, plus 1 minus p sub s into the log of n minus 1, where n is the cardinality of the set on which x takes values. Now, why is this inequality important? The reason why it is important is that you have this celebrated Shannon's noisy channel coding theorem, and you can prove the weak converse of it using the classical Fano inequality. What it says is that the number which Shannon gives, which is called the capacity, you can't beat that number, and this inequality gives you the proof for that. Because if you try to beat that number, then the probability of error is going to be bounded away from 0, and our requirement is that the information has to be transmitted reliably across the channel. Now, I am going to do the same thing for the quantum case, and this work was done by Schumacher. What he said was that he basically, instead of using the probability of success, he was using the entanglement fidelity, which is defined like this, where RQ is basically the purification of Q, and R1 Q1 is equivalent to R dash Q dash, which I had before. So, instead of R dash Q dash, you just put R1 Q1 there, and that is the entanglement fidelity. And you can also define a quantity called entropy exchange, which is just the von Neumann entropy of the composite system R1 Q1. Now, what Schumacher did was he gave a inequality which is now called the quantum Fano inequality, and that upper bounds the entropy exchange by a function of entanglement fidelity as this particular form. Now, if you just look at this form, it is the binary entropy function of the entanglement fidelity plus 1 minus entanglement fidelity into log of d square minus 1. It is strikingly similar to what you have over here, except that instead of n over here, you do not have a n, you have a square of that, square of the dimension. Now, because it satisfied the quantum Fano inequality, many people they argued that the entropy exchange might be like the conditional Shannon entropy in the classical information theory. So, they defined what they called as the coherent information, which I defined before, and there was a conjecture that perhaps this is like the capacity, and Peter Shor actually proved it in 2002, 7 years after this guy gave this inequality. Now, I was going, there was a generalization of the classical Fano inequality, which was given by Hahn and Verdu. These are well known information theorists. So, I was looking at this paper, and after I read that paper, I was asking myself that can I do the same thing for the quantum case, and it worked out. And so, I gave extensions of the quantum Fano inequality and various Fano like upper bounds to the entropy exchange. So, one of the bounds that I gave was that you have this free parameter, which is any probability vector gamma, and you get an upper bound like this. Now, where lambda i's here are eigenvalues of rho, and if you were to put your gamma I, if you were to choose them to be 1 over d, then it would give you back the vanilla quantum Fano inequality, but actually you can do more. You can actually because this is a stronger version, you can make the bound even tighter. Now, it is easy to see, this is, I already said that that the vanilla QFI is a special case of the above, and our approach also gave an alternate derivation of the quantum Fano inequality. Then I wanted to think about whether this can be used to maybe give a stronger converse, or how I can use this inequality, and then I got involved into other things, but I'm still thinking about it. So I don't know whether we can give a better converse or not. And I'll just go through this figure and then I'll end this talk. So here you have the entropy exchange, and there is a some parameter p. Actually, it's the probability for a depolarizing channel, and this probability indicates that you are going to replace your density matrix with I over d, which is another density matrix, but which has no connection with the original density matrix. And you can just ignore this. This basically is the proposed Fano inequality, and this is the true value, and this is what the Fano inequality gives you. So if you see from here, the proposed inequality is actually much closer. It gives a much better upper bound to the entropy exchange than the Fano inequality. And that's where I'll end the talk.
We have time for a couple questions.
My question is this, that often in the short term certainly, it's not necessarily the mathematical details, but it's a certain intuition behind the work which tells you now where should we go beyond where we stand at this particular point. And I'm not suggesting that one can guess as to what results may be discovered, but if one was able to articulate this intuition, then possibly certain larger map of what one ought to be doing in the near term would become clear.
I can try answering this question, maybe taking an example of quantum algorithms. Not many quantum algorithms are known. Also, it seems to me that the intuition which we have derived by designing classical algorithms for classical computer science over the last several decades, that intuition doesn't really carry over to the quantum world. How do you design new quantum algorithms? It's not very well understood. And in some sense, it's also a good news, because it's anybody's game. It's not that computer scientists can only jump in. I mean, anybody who has a reasonable understanding of this whole setup, the mathematical setup, could perhaps come up with a new algorithm. So maybe that's a there's a lot of space, it seems, over there, although nobody knows how to tap that unknown space, but that seems to be quite exciting. I don't know if I answered.
Okay.
Any other question? Yes.
Do you know what they use it for, or are there some applications that you might be able to use yours for? Or?
Yeah, I would be happy to talk to you, but I don't know right now. For example, I don't know whether they have used it to give a better converse to the channel coding theorems. I don't think they have done that. And also another thing was that, which was kind of a, I don't know whether that's really true, but see, when p goes to 0, which is where you have the probability of error is going to 0. Now here, the bounds which I give and the vanilla quantum Fano inequality, they are almost coming out to be similar. Now this is only a plot for the depolarizing channel. I can't generalize it to other channels, of course. But if that statement were to be true, that when your fidelity is approaching 1, then the proposed one and the vanilla Fano is nearly the same, well then it would mean that probably you can't use it. But I don't know that answer now. I mean, that's my, yeah.
All right, thank you very much once again, Dr. Naresh.